On the previous page, I mentioned that our goal is to find lambda and phi such that for matrix A, we have AV equals to lambda phi. So it's very important here that phi is a non-zero factor. Okay, it's not a zero factor, because otherwise this equation will be too easy to solve. But then before I tell you how to find lambda and phi, firstly, let me introduce some terminology. It turns out both lambda and phi has a name. So for example, lambda, so the lambda here, it's called an eigenvalue of A. Okay, eigenvalue. So look that this is a German term, okay, this is a German word, and it's pronounced as eigenvalue. And how about phi? Phi is called an eigenvector, okay, eigenvector of A, but with respect to this eigenvalue, with respect to lambda, with respect to the eigenvalue. So just terminology, eigenvalue and eigenvector. So rather than calling it lambda and phi, we call it a special name. But now come to the main dish. How do we find lambda and phi? And now it comes to theorem 11.3.1. This is very important. Okay? So let me tell you how to find lambda. So let me write down. So how to find lambda? How to find eigenvalue? So it turns out, how do you find lambda? It's by solving a polynomial equation. So we're going to solve the equation determinant of a minus xi equal to 0. Okay? So this is how we find lambda. And then, so eigenvalue. This is how we can eigenvalue. Eigenvalue. How about eigenvector? Eigenvector. For each eigenvalue, how do I find the corresponding phi? So how to find phi? It turns out to do that, we just need to solve a system equation. What's the system equation? The equation is a minus lambda I and then 0 on the right hand side. So we need to solve a linear system equation. So this is very important. How do you find eigenvalue and eigenvector? Eigenvalue come from the root of a polynomial equation a minus xi determinant. And the eigenvector is by solving a linear system equation by Gaussian elimination. Okay, so by Gaussian elimination. Of course, this looks far too abstract. So let us do a concrete example together. So example. Find the eigenvalues and eigenvectors of this matrix 7, 2, 2, 4. So firstly, let me compute eigenvalues. Eigenvalues. So how do I compute eigenvalues? The way to do it is to solve, okay? Solve determinant a minus xi. Okay, in this case, I is I2. So what do I mean a minus xi? So let's do it slowly. Determinant of a is 7, 2, 2, 4. Xi, well, what's I2? I2 means 1, 0, 0, 1. And then you multiply by x, that means that you get x0, 0, x, okay? So minus x0, 0, x. How do you subtract matrix? Well, subtracting matrix is like subtracting factors. You do it component-wise. So this becomes determinant of 7 minus x. 2 minus 0 is 2. And then 2 and 4 minus x. And how do we compute this determinant? Well, AD minus BC. So we have 7 minus x, 4 minus x, and then minus 4. If you spell that out, okay, this would give you x squared minus 11x plus 24 back, okay? And if you factorize it, okay, factorize it by using high school method, you will have x minus 3 times x minus 8. And our goal is to solve this polynomial when it equals 0. So we have, of course, x equals 3 or x equals 8. And these are the eigenvalues. So the eigenvalues are 3 and 8. Okay, so that's it. Okay, to solve eigenvalues, you just need to solve the equation determinant of a minus xi. But what do you mean by a minus xi? That means that you subtract x along the diagonal. So if you want to do it quicker, basically subtract x only on the diagonal and then spell out the determinant. Then you will obtain an equation in x, and now you ask yourself, what are the value of x such that this will become 0? And it turns out in this case, the eigenvalues are 3 and 8. Okay? So, eigenvectors. Eigenvectors. We have two eigenvalues, so we need to do it one by one. So the first eigenvalue is lambda equals to 3. Okay? The system equation that we want to solve is a minus 3i and that's 0 on the right. But what does that mean? Okay, what does that mean? So a minus 3i, so you subtract 3 on the diagonal, then you get 4, 1, and then 2, 2, and then 0 factor on the right, so 0, 0. By Gaussian elimination, I would like you to check, okay? This is not difficult. Gaussian elimination. Eliminated, you will get 2, 1, 0, and then the second row becomes just the 0, okay? Therefore, the second equation uses, the second equation tells you 0 equals 0. The first equation tells you that 2x plus y equals 0. So we set x to be t, then y will equal to minus 2t. So what are the solutions? The solutions are, okay, the solutions are t, comma, minus 2t, and t is real. But of course, you can take out t as a common factor, so t, 1 minus 2, and t is real. And of course, this is the span of 1 minus 2. The linear combination of 1 minus 2 is exactly the scalar multiple of 1 minus 2. But that means that this is one of the eigenvector. Okay, so our convention is to write eigenvector as column vector. So 1 minus 2 is an eigenvector of A with respect to the eigenvalue lambda equals 3. But you may ask, do I have to take 1 comma minus 2? Actually, no. You can take any multiple of it, okay? Because you can take anything here as long as it's not still factor. So, indeed, we can take any multiple, any non-zero multiple, let me emphasize that, any non-zero multiple of 1 minus 2 as the eigenvector. Okay, let me make this smaller. Because this is only one of the eigenvalue. We have another one. The other eigenvalue is h, so we have lambda equal to h. To find eigenvector, we need to solve the system equation A minus hi, and the zero factor on the right. But this will give me a system of the form, okay? So A minus hi, so I subtract 8 from the diagonal entry, so I get minus 1 and 4, and then 2, 2. And the zero factor on the right, so 0, 0. And then if you apply Gaussian elimination, so check, okay? You obtained minus 1, 2, 0, 0, 0, 0. Therefore, in this case, we have minus x plus 2y equals 0. So how do we solve that? If we set y to be t, then x equal to t. Therefore, what are the solutions? The solutions are, so I'm going to do it quickly. It turns out the solutions are given by the span of 2 and 1. I will let you check, okay? Check. And therefore, what is an eigenvector for, in this case, an eigenvector is given by 2, 1. So 2, 1. So usually we write it as column vector. So 2, 1 is an eigenvector of A with respect to the eigenvalue lambda equals to 8. Again, you don't have to take 2, 1 here. You can take any scalar multiple, any multiple of it, and that would be fine, as long as it's not a zero factor. So this is an example of how to find eigenvalue and eigenvectors. And on the next page, we do more examples.